This is the solution of question 1 of homework 5. In this question, we are given two independent random variables x and y. X is uniform in 1 to 2 and y is uniform in 0 to 1. So for z equal to x plus y, we have to find the PDF of z. So for this kind of questions where z is a function of x and y, so we have to first find the CDF of z, which is usually in the form of the double integral of fxy of x comma y, the joint PDF of x and y, where the limits of x and y depends on the question. We have to substitute the correct limits to get the solution. So here, so z is x plus y, x and y are uniform, so this is the plot for x and y. So clearly we can see the boundaries for z. Z is greater than 1 and less than 3. So we have to take two cases. One is z is greater than 1 and less than 2. The second case is z is greater than 2 and less than 3. So the first case happens in this region, in this lower half of the square, this triangle, and the second case happens in this part. So for the first part, we have to find the limits. For some z, let us fix a value of z. For some z, x is z minus y. So fz of z is double integral fxy x comma y dx dy. So for the limits here, x is running from 1 to z minus y and y is running from 0 to z minus 1. So x is 1 to z minus y because x is uniform in 1 to 2. So x starts from 1, and since z is fixed over here and x is z minus y, x limits are x equal to 1 to z minus y. And for y is uniform in 0 to 1, so its limits has to be in the form of 0 to some value. Since z over here is less than 1, it's greater than 1 and less than 2, if you subtract 1, we see that z minus 1 is greater than 0 and less than 1, so which is similar to the limits of y. Therefore y is running from 0, the value of z is fixed over here, therefore y is running from 0 to z minus 1. So if we compute this integral in this region, since it is uniform, fxy is 1. If we compute this integral, we get the CDF z minus 1 whole square by 2, which is for this region only. So now we find the PDF, which is just the differential of the CDF. So differentiating with respect to z, we get fz of z is z minus 1 for region z greater than 1 and less than 2. Now for the second region where z is greater than 2 and less than 3, we need to find the area of the shaded region. So instead what we'll do is find the area of the unshaded region, because it's a triangle and it's easier to compute. So the shaded region is p of z less than or equal to z. What we do is, which is equal to 1 minus p of z greater than z. So first let's compute p of z greater than z, which is this region. So again over here z is fixed, it is between 2 and 3. We have to find the limits for x and y. So x was initially 1 to z minus y, but over here, since x is uniform in 1 to 2, the lower limit will be z minus y and the upper limit will be 2. Similarly for y, z is greater than 2 and less than 3, so we subtract 2 from both sides. So if we subtract 2, we get the z minus 2 is greater than 0 and less than 1, which is similar to the limits of y. Initially we took the lower case or the lower half, now we take the upper half, so we get z minus 2 to 1 and z minus y to 2. Solving this integral, we get this. So here is a big integral, so I solve it here. So we get the CDF z minus 2 whole square by 2 minus z square plus 5z minus 9 by 2. So now we differentiate this with respect to z, and we get 3 minus z. So we computed the two regions where z is defined, and we found the complete solution for the PDF, which is fz of z is z minus 1 for z greater than 1 and less than 2, and 3 minus z for z greater than 2 and less than 3, and 0 otherwise. So if we plot this, we get a triangle. So intuitively this is a correct solution, because the uniform is a rectangle pulse So convolution of two rectangle pulses gives us a triangle. So in the next, another way of solving this is exactly by convolution. In the convolution method, so if x and y are independent, then only we can use this. So fz of z is integral fx of x fy of z minus x dx. So we have to be careful with the limits of the integral over here. So initially we have seen that there are two regions for z, z greater than 1 and less than 2, and z greater than 2 and less than 3. In this region, fz of z is integral. So since we are integrating with respect to x, our limit should be dependent on x. So x is uniform in 1 to 2. So therefore the lower limit is 1 and the upper limit is z for some fixed z. So integral 1 to z, this integral will give us the CDF for the first case. We integrate this, we got z minus 1. The second case, z greater than 2 and less than 3. Similarly, over here the upper limit for x is in uniform 1 to 2, so the upper limit is 2, and for some fixed z, the lower limit is z minus 1. So x run from z minus 1 to 2, fx of x, fy of z minus x dx. So this value is 1 in this region, therefore integrating we get 3 minus z, which is consistent with the method, is the geometric method, but this is easier to solve for these kind of questions. But this is only possible if x and y are independent.